again, we talked about yesterday, or was it on Monday probably, that in the Nordic system, this is a picture of southern Norway, the border to Sweden. There is a high focus on the power transmission corridor between Norway and Sweden, because there is a demand from the power market to export hydropower from west to east, you might say. Also from the west to the south through the HVDC links to Denmark and Germany and to the Netherlands. Germany link is not ready yet, but it's coming. But the transfer capacity is as limited as I explained. You could have thermal capacity limits, voltage. The eigenvalue analysis is that we have modes around 0.3 hertz. We have a mode at 0.5 hertz approximately, and we have several modes at higher frequency. Now, the two that are of interest in this study that we will see later is at 0.3 and 0.5 hertz. And in order to classify those, we do a modal analysis. And if you look at the 0.33 hertz on this huge model and plot the eigenvectors, the elements of the eigenvectors related to speed of the generators, you see that we have a bunch of eigenvectors that point in the same directions, or eigenvector elements, I should say. It's not that they are not. They are complex numbers. They are elements in the eigenvector. They point in the same direction, and it turns out that they are all related to generators in the Finnish grid. So, I mean, I don't expect that you are very, very well known about the geography of the Nordic countries, but let me try to draw it. We have. This is Norway, this is Sweden, this is Finland, and this is the Baltic Sea. This is sea, and Russia out here, and these are our corridor about here. But there's also sort of a corridor up north to Finland. So you might say that Finland is at the totally opposite end of the power system. Therefore, you have low frequency oscillation between them. And the Finnish generators are sort of usually in opposite phase to the rest of the system at 0.33 hertz. If we look at the 0.5 hertz mode, we see a little bit more complex pattern. But it is clear that all the generators in southern Norway is in phase at that frequency, and they are almost in opposite phase to southern Sweden and Denmark. Denmark being down here, of course. So you might say that we're talking about computer analysis. Later we will see that what we can do also online with phasor measurements. But what you want to do then to assess where is the limit is to sort of like 3 seconds. Or even at some point more when it starts to get transient and stable. But up here You see it's a 0.3 hertz mode. So it verifies that you should not go about 2,200 megawatt at least. In this case, we tested this also for the transient. I mean, if you some kind have some mean have the linearized system model, you can do this very easily also in MATLAB or other programs. Our factory has a fairly good tool for small signal analysis, so I can demonstrate that later. In PSSC, there are some methods available, but you could also use other methods, such as the Prony method, to identify critical modes. An example of a Prony analysis is here, and I'll also come back to Prony analysis later when we talk about PMU applications. The Prony methods is based on that there has been a kind of disturbance, so you have an oscillation that has a certain ring down, as we would call it. And I mean, that is the Prony method, so that you try to try to fit such a function to your signal and obtain the sigma and the omega and the theta. If you have to, you could also sort of estimate the mode shapes by comparing the phase shift and the amplitude of the signal. So, I mean, PSSC, for example, has a tool for that. It's not possible to see, but if you go closer, you can see the ring down here, and how you select the window, and you get the number. You get sort of the best estimate of the eigenvalues for that signal. So, introduction, but it's the basis.
Was in the range of
yeah.
0.55.
Yeah.
Generally, the inter-area mode is between 0.1 to 1
yeah.
hertz, and
You have to deal with it locally. Was that an answer? Somehow? Okay. We can keep on a little while before we take a break. So the plan is now that I will give you an overview of the subject related to wide area monitoring and application of phasor measurement units, and then, as time allows, we will go a little bit more in detail into some of the application that is relevant, that has been developed, show some examples of tools that we have implemented, and that will be today and tomorrow, since the frequency is usually 0. But some relevant, more variability in higher resolution of our measurements, and synchronized measurements is one of these things. And there's also that we see clearly more need for automatic control, because at some certain point things cannot be managed by the operators manually. You need automation. So in that sense, the new technology that is put forward by phasor measurement units, for example, is interesting. So if you look at see power oscillation and how things work, having the information in a digital form, you don't really do that. But that was the future, digital instruments, and then you got sort of what we should call now fairly modern SCADA, where we are introducing into the SCADA AMS system also phasor measurements. So today we are at the stage that we are searching for good application of PMUs in monitoring of specific conditions. And those are what we will call the wide area monitoring systems. How do we utilize the enhanced information in the control room given today's technology? And in the research we need to look into the possibilities of the future. And what we are sort of envisioning there is more sort of in terms of live simulators, autopilots, things that can tell us immediately what is wrong, point to where we need to do controls, etc. So this is the sort of what you have to envision when you are working in this area now. How can this be utilized in the future where we have all this information, we have communication, we can measure most things, we can control many things. That's the motivation. How do we get to the future control center with all this live information that can be sort of it's a way in a way it is from going from black and white television to nowadays high density HDMI world. It's another dimension to anything. The resolution is much higher. Okay, again, just to say a few words about our challenges. Here's the Scandinavian or Nordic system again. In Norway, we have control centers in Oslo, the capital, and also one up here in the far north. And they are controlling the entire grid. The distance here is 2,000, more than 2,000 kilometers. It's a fairly long distance. Low populations in the northern areas, but the lines are long. So it's dynamic system. I said this, I showed you before, so I won't bother you with this again, but it's about monitoring with the aim of improving the stability limits. So we need to determine the capacity limits. We need to be able to monitor them in real time and then enforce the power transfer limits online or even improve them with better controls. And the background for this is as I have been touching upon, that traditional SCADA EMS is rather slow, focus on steady state. You have updates with different sampling rates, could be maybe from minutes somewhere up to maybe down to 1 second or something. But it's not synchronized, and the measurements are coming in when they're available. So that must have focus on the steady state. But as we have seen, the power dynamics can be much faster than 1 second. So we need an enhanced information that is available with phasor measurement units. So you could use that with respect to determining the limits. You could, for example, use phasor measurement for state estimation. You use wide area monitoring tools to manage to monitor your limits, or to know your limits. And you can develop wide area control technology to hopefully increase the limits. So that's the starting point. That's the possibilities that we see and the challenges. So what can we do then? So first, I guess since you went to this course, that you all sort of know what a phasor is, but still I always take it with me because I know that many people talk about PMUs without knowing what a phasor is, and that's not good. So, but we are used to the concept of phasor from our calculation when it comes to AC grids, right? So, but in principle, the phasor concept is just a way of representing a time-varying signal. A time-varying signal has an amplitude, and it has a phase angle with respect to something. You can always discuss that what the reference angle is, and you can vary that, but you have to have a reference for angles. And with that sort of reference, you can draw the phasor as a complex number with an amplitude and phase angle. But the interesting thing is that if you have two measurements, of course, or more, because then you're able to measure the phase angle difference between the phasors. And that is the strength of PMUs, of course. That the measurements are synchronized so that you can measure the phase angle correctly or with a good accuracy to place them in the same phasor diagram, even though they might be hundreds of kilometers apart. That is done by GPS or corresponding synchronization. And then one would ask, why do we care so much about these phase angles? And I think you have seen that from the first days here, that these phase angles, they matters a lot in AC systems. And the simplest way of sort of explaining that is just to look at the power transfer on a AC line, where actually the power flow is more or less proportional to the voltage angle difference between the two nodes. So two large angles is critical. And the ability to measure those angles give you better information than just measuring voltage and current. Even though you could, of course, what you do partly today is that you estimate the voltage angle by the state estimator, because you are able to measure voltage and current, so you can compute power. But still, that is not within the resolution, so that you can capture dynamics in a good way. So that is the definition. The phasor measurement unit then is in principle like this. you get your analog inputs, voltages. See, I have forgot to translate this. Voltage or current, three-phase or single-phase, depends what you want to do. You need to condition the signal, of course, filter, and you need the analog to digital conversion. And then the point is that the measurements are synchronized through a phase-locked oscillator that is being triggered by a GPS signal, so that you have the synchronization done there. And then there is a processing, basically a kind of Fourier transform-like processing to get the phasors out. You could say, in principle, normally one phasor per period. So resolution of the phasor measurements could be up to 50 samples per second. Sometimes also it can go up to 100. But I would say that I mean, the definition of a phasor in less than one period, it's a little bit fussy to me, but okay, you can do it. Then, of course, the good thing is that what you need to transmit or to, and then you would normally send the measurements to what we call a phasor data concentrator, which is another computer, perhaps connected to a database or a storage, so that you align the phasors from all the PMUs in a synchronous way. So if you, I mean, they have an IP address or something, 241, and they stream the data, all of them, into a PDC. And this will align the data with a time, phasor 1, phasor 2, phasor 3, and the variables here. 2, 3, 4, 3, 6, 9, for all the PDC. So if you're and then this could communicate again with another PDC in another country that has other PMUs coming in.